Okay, good evening everybody. This is going to be a big mega live stream. I'm going to be going through a whole AQA paper of questions which are the kind of similar style to what might come up in paper 2 next week. So this is going to be based on the Physics and Maths Tutor Education, the PMT predicted papers that they put out there. You can download them freely from the PMT website. And basically what I'm going to be doing is going through the whole paper, having a go at the questions, talking about the physics behind it. Also, I do have, as you can probably see in this big red bar at the bottom of the screen, I do have some masterclasses I'm doing. I've got one for AQA tomorrow. That's going to be Wednesday from 7 o'clock. So you can book onto that by going to my website. So you can just head over to alevelphysicsonline.com. And you can kind of book on there. You can also, and I know some people have exams tomorrow, so I know there's probably not going to be a huge number of people actually watching this live, but this will be up after the event for you to kind of catch up whenever you need it. I've also got another masterclass coming up on the weekend, so on Sunday morning between 10 and 12, I'm going to be doing that masterclass again for AQA. So yeah, for most people out there, I appreciate that a lot of you do have maths tomorrow, and this was kind of probably the best time I could do this because I'm doing live masterclasses Thursday and Wednesday this week. So of course, it's great to see so many people in the chat. Again, people who were here last night as well. But if you're not watching it live, that's absolutely fine. But obviously, you can re-watch this anytime you want over the next few days. So appreciating there probably won't be a large number of people watching this live because most people who do A-level physics tend to do A-level maths as well. Let's just begin, shall we? So there's some stuff there about the person who wrote it. Okay, what do we mean by capacitance of 0.050 farads? So I would be looking at this one here. It's a 2-mark question. I'd probably be looking at the data sheets. Now, obviously, you're going to get the bigger one that you get in your exam. We can see that capacitance is equal to Q over V. And therefore we can really define capacitance as the charge stored per unit potential difference. So we can say that this would mean this is equivalent to 0.050 coulombs of charge stored per volt. Okay, so something along those lines would be what the answer is. But then you need to sketch a graph on the axes in figure 1 to demonstrate how the charge on this capacitor varies with PD across the range provided. So of course, the size of the capacitance will always stay the same, because this is going to be 0.050 farads, but we're going to look at maybe a point here at 10. So we want to look at the charge. Now, of course, the charge is going to be equal to the capacitance times the potential difference. The capacitance is 0.050. When you've got a value of 10, that means the charge stored is going to be 0.50 coulombs. And therefore this point here is going to be 0.50 when that's 10. And of course we can see that the charge stored is going to be directly proportional to V. So there's going to be a straight line back to 0. So I'll be doing this, probably doing everything in pencil and taking this line back to the 0 point over there. So that would be what it looks like. The appropriate scale, I'm going to put a few more values on. 0.30, 0.20, 0.10, 0.00. And there we go. I think that's enough. We've got a straight line that goes through the origin. I've drawn it in with a ruler. And then, of course, we've got an appropriate scale. So they're the kind of things that are going to get you the marks. Okay. By the way, is anybody watching this tonight who doesn't have an A-level exam tomorrow? Is there anybody out there who does A-level physics but doesn't do A-level maths? Okay, the next question says, explain how the graph can be used to determine the energy stored by the capacitor for a given potential difference across its plates. Okay, Sam, hello. You are one of the few people here tonight. Hello, Sam. Hope you're doing all right. Okay, so we need to look at the energy, and basically the energy stored is going to be equal to the area underneath that. Okay, again, there's a couple of equations that you might be familiar with for AQA in particular. So it says here, where are we? Looking at the energy is equal to a half QV or a half CV squared or Q squared over 2C. Okay, so there's different equations that we can use to actually work out the area underneath that line. So, explaining how the graph can be used to determine the energy stored, you basically calculate the area under the line up to that value of potential difference. So that would be my approach to it. Okay, so you just need to calculate the area underneath the line to look at the energy stored by that capacitor. Okay, a capacitor of 350 microfarads, so we often have very, very small numbers for the capacitance. We've got it charged to PD of 8. It then is discharged through a resistor. Calculate the energy stored by the capacitor once it is completely charged. So we've got the capacitance, we've got the value for V, and therefore we can say that the energy stored is equal to a half CV squared, which is 0.5 times 350 times 10 to the minus 6 multiplied by V, which is 8, and that's going to be squared. So this would be my approach. And by the way, I haven't actually worked through these questions yet, so a lot of this is stuff that I'm hoping I get correct. So 0.5 times 350 times 10 to the minus 6 times 64. So that's equal to 0.0112. So I would probably give the energy stored as 0.011 joules. Okay, so I'm going to give this to two significant figures, like the raw data that we have up here. And actually what you'll notice is that the fact it's gone and discharged through this resistor is kind of irrelevant for this part of the question. The only thing we need is a capacitance and the potential difference that it's been applied to. Okay, Phantom Plays says science is better than maths 100%. I think, yeah, Sam, why do they add irrelevant bits? Sometimes they just add irrelevant bits because it's like the challenge is, can you look at lots of information and interpret what is important for that? So sometimes they will add stuff. Not often though, to be honest. It's not often they give you completely irrelevant information, but potentially, I haven't actually seen the next question, but potentially that could be asked on a subsequent question, maybe to work out the time constant. Oh, here we go. That's why it was given to us. Determine the time constant. So the time constant of the circuit, tau, is going to be equal to RC. So in this case, yeah, so actually I probably shouldn't have taken that out. So the time constant is the resistance times capacitance of that bit of the circuit where it's discharging through. So that's equal to 450 times 10 to the 3. Because we have a high resistance in kilo ohms, we're going to multiply that by the low capacitance of 350 times 10 to the minus 6. Okay, I'm just going to go back into the blue pen to make my answers kind of stick out. And therefore that's 450 times 10 to the 3 times 350 times 10 to the minus 6, which is equal to 157.5. Now, because it's a time constant, the units will be seconds. And I'm going to give my answer. I guess that's three significant figures and that's three significant figures, because in the kind of the rules of A-level physics, a trailing zero adds to the significance. So I'm going to give my answer as 158 seconds. Okay. Right. People find chemistry and maths miles easier than physics. Yeah, I think it just depends on the way that your brain works. I found at school that the chemistry was my most difficult A-level. And I probably found the maths easier than the physics. And I think I like the maths because there was less writing, whereas I do find physics is a bit more difficult when you've got to explain yourself. Yeah, but I'd say that the maths in A-level physics tends to be relatively straightforward. Find the PD across a capacitor 60 seconds after discharging has begun. So what we're going to have is, I'm just going to draw a graph to try and visualise what's going on. We've got the initial value that it was at, V0, and if we look at V against time, we're going to find that there's this kind of exponential decay. So we want to find what the value of V is after a time of 60 seconds. Okay, so in order to work this out, we aren't actually given the equation. I think for AQA they just get given the equation saying Q equals Q0. So we can also say that V is equal to V0 times e to the minus t over RC. Okay, so we know the time is 60. We've worked out the time constant up here as 157.5. We know the initial value was given to us because it was charged up initially to 8 volts. So we can say that V is equal to 8.0 e to the minus 60 over 157.5. And I'm going to be using my calculated value in this part of the calculation over there. So we've got minus 60 divided by 157.5. We're going to do e to that number times 8 gives me an answer equal to 5.466. So that's two significant figures. So I'm going to give my answer as 5.5 volts. So is that the right answer? Okay, is that the right answer? Yeah, I think that looks to be good, just looking at the answers they've got here. So yeah, so they've given it 5.47, but 5.5 would be an appropriate answer for that question. So that first one there wasn't too bad. Yeah, cool. Okay, let's look at some gravitational fields. Now, of course, although this is aimed at AQA, a lot of the kind of questions here will also be useful for anybody doing OCR or potentially Edexcel or EduCAS or WJC. It's all just kind of good kind of A-level physics. So gravitational potential. What I would be doing is I'd be looking at my data sheet that again is given to you in the exam. And the equation that might be useful is the one where gravitational potential V is equal to minus Gm over R. So this is just for me to just try and work out, okay, that one there, the V stands for the gravitational potential at a point. And yes, this is A-level, so if you're a GCSE student, don't worry, I'll be doing some more live streams for GCSE, but I've got plenty of stuff over at GCSE Physics Online. But this one here gets a little bit beyond the kind of level of GCSE. Okay, Octavian says, the work done in bringing a particle from infinity to that point. Something like that, something exactly like that. So the gravitational potential is the work done per unit mass in bringing the work done per unit mass in bringing an object to that point from infinity. I think that would be my answer. Yeah, so basically it's not the work done, it's the work done per unit mass, and I think that's the key thing. Okay, if we're looking at the gravitational potential energy, that would be the work done, but this is, because it's potential, it's going to be per unit mass or per kilogram. Okay, so you have to say per unit mass to get the mark. I think the mark scheme they've got here, let's have a look at what they said. They said the work done in bringing a kilogram mass from infinity to that point. Yeah, that would be absolutely fine as well. So I'm just going to say per unit mass. Yeah, right. We then have the gravitational potential at various distances are from the centres of Earth. Okay, so we're going to use this equation up here, I suspect. Given that the data is consistent with a relationship V is proportional to 1 over R, complete the rest of the table. So, actually, yeah, that's important. So because we know that V is equal to minus Gm over R, if you've got something around the same planet, like the Earth, it's going to have the same big M, the same mass, and G is going to be the same, and therefore we can say that V times R is equal to a constant value. Okay, so basically this number times this number are going to be a constant value, so let's just work that out. I'm just going to multiply the two things. Well, basically what we can say is that, like, let's imagine that's row 1, that's row 2 and row 3. We can say that R1 times V1 is equal to R2 times V2. So if we want to work out this, which is going to be V2, V2 is going to be equal to R1 V1 over R2, which in this case would be 7500 times minus 5.36 divided by 12,500. Okay, so basically, because VR is a constant, then this times that is equal to this times that, which is what I wrote down here, and I just labelled the rows in this stuff here, and therefore we can work out what V2 is. So if I just put the numbers in, this is minus 3.22. So I'm just going to give that to the same number of significant figures as that one there, just to sort of keep it consistent. And then the next one, V3, is going to be equal to R1 V1 over R3. So that's going to be 7,500 times minus 5.36 divided by 22500, which is minus 1.79. So that's kind of my V3. So basically this and this are the answers. Is that right? Yes, that's right. Of course. Okay. Hopefully that's all making sense. So this question, it wasn't really about gravitational potential. This question more was like a mathematical question about the relationship between these two different numbers. Okay. We've then got a satellite of mass 500 kilograms. It's moving from an orbit of radius 1250 to 12,500 to 22,500. Show that the potential energy of the satellite increases by 7 gigajoules. So if there's questions like this, my approach, I'm just going to get a compass. Okay, I do think sometimes it can be useful to actually draw a diagram. So I'm just going to draw a diagram to the side just to help me, well, help you, I guess. I'm just going to put the outer orbit, the inner orbit. Oh, messed that up, haven't I? I hate using compasses like this, especially the cheap school ones. Absolutely rubbish. Okay, so basically we've got the planet Earth in the middle. We've got the satellite at that position, and then it moves up to this position up here. So we've got the mass of the satellite is 500 kilograms, and basically it goes from this inner orbit, which is 12,500, and it goes up to this outer orbit, which is 22,500. So we've got basically a bit of a visualization of what's going on. Now the potential energy is going to increase because it's going to have a difference in its gravitational potential. So the change in gravitational potential, is going to be equal to, let's say, 3.22 minus 1.79 times 10 to the 7 joules per kilogram. So let me just work that out first of all. So that's going to be equal to 1.43 times 10 to the 7 joules per kilogram. But that means the change in gravitational potential energy is going to be equal to this change in gravitational potential multiplied by the mass, because that's going to be the energy per kilogram, but the actual satellite has got a mass of 500. So we're going to say that's 1.43 times 10 to the 7 times 500, which is equal to 1.43 times 10 to the 7 times 500, which is 7.15 times 10 to the 9, which is approximately equal to 7 gigajoules. Okay, so this one here was a show question, and what we had to do was show that the energy is about 7 gigajoules. Okay, the triangle, phantom, just means change in. And what we're interested in here is the change in gravitational potential energy as it moves from one height to another height. Okay, so it's the change as it goes from the inner orbit to the outer orbit. Phantom, hopefully that helps. Okay, right, the next one. These are the ones that they do get a bit tricky, so I've really got to sort of try and think about what's actually happening. Okay, it says that the kinetic energy of a 500 kilogram satellite orbiting the Earth with a radius is 7.96 gigajoules. Okay, so basically that's got an energy of 7.96 gigajoules. Okay, so I'm just going to put that number on here. Calculate the kinetic energy of the satellite when it is in orbit of radius this. So we need to work out the kinetic energy at this point. So so my approach would be to use, so this is something that AQA doesn't actually give you. It doesn't give you an equation for the energy of a satellite, but it's something we could work out. We could probably go back to first principles, so I'm just going to use green to show this. We know that as it's moving around at this point over here, the force on it is going to be causing this centripetal force mv squared over r, and that's going to be equal to gmm over r squared. Okay, so what we can do is we can take these two equations, we can cancel that and cancel that and cancel that and cancel that to say that v squared is equal to gm over r. Okay, but of course the kinetic energy is equal to a half mv squared, and so that's going to be equal to a half times the mass times v squared, but v squared is equal to gm over r. And so another equation we can use for a satellite, if we want to work out its kinetic energy, is the kinetic energy is equal to gmm over 2r. Okay, so we can now put some numbers in. So the kinetic energy is going to be equal to 6.67 times 10 to the minus 11. So that's big G. I'm just checking my numbers here are correct. We've got the mass of the Earth, which is given to us in the data book as 5.97 times 10 to the 24, but I'm sure you kind of probably remember that. We've got the mass of the satellite is 500. We're going to divide this by 2 times the radius, and the radius is now 22,500, so that's 22,500 kilometers, so that's times 10 to the 3. So this is kind of basically a big long equation, but this is what I'm doing. This Quinix, this is actually the predicted paper that PMT have put out. So you can find this for free on PMT. If you do want to, by the way, if anybody out there is watching this and you want to find AQA papers, you can find them on my website. So this is A-Level Physics Online. You can see I'm doing masterclasses quite soon. But if you go to the AQA page, as you scroll down, you can see past papers and work solutions, and basically you can find my work solutions. So let's have a look at A-level AQA paper 2. You can see I've got work solutions that you can download. I've also got video walkthroughs. So basically what I've got are walkthroughs of the AQA papers. I've got paper 2 from 2023, and I've got paper 2 from 2022, and also one from 2020, and I'll be adding more as time goes on. So hopefully that can be quite useful as you're preparing for your exams, I guess later this week. Right, do I have explanations for each chapter? Oh wow, we do have, okay, a university astrophysicist here. Okay, I've got a question for you. No, I don't. I think it would just be too mean, because it's something that I couldn't work out the other day about. Okay, do you know what? It was a. Okay, so for the person in the chat who's a university astrophysicist, myself and Zed Physics, who also makes videos, we did a question from an Olympiad paper, and there's a question that we had where it was about the kind of Kepler's law and how t squared is equal to gm r cubed over 4 pi squared, I think it is. But if you've got two different masses, do we just say m is a combined mass of the two things which are orbiting each other, or do we just assume that one thing is much bigger for Kepler's third law to apply? Anyway, it was something that me and Zed Physics talked about. We addressed it slightly in the video, then we kind of skirted the issue, but that's something that as physics teachers we didn't really have a good answer to. Anyway, it's a great question all about the DART mission. It was really, really good. Right, so let me just work all of this out. So I'm getting a number equal to 4.42 times 10 to the 9. So that's a number I've just calculated. So the kinetic energy, okay, that's 10 to the 9, and that's given in gigajoules. So my answer would be 4.42 gigajoules. Okay, I think all the other raw data is to 3 significant figures. So that would be my answer for that. Okay. Right, calculate the magnitude of the difference in kinetic energy of the satellite when it moves from 12,500 to 22,000. Calculate the magnitude of the difference in kinetic energy. So I guess the change in kinetic energy is just going to be equal to this value, 7.96 gigajoules. Take away the new value, 4.42 gigajoules. So that's 7.96 minus 4.42, which is equal to 3.54. Is that right? 3.54 is just a change in kinetic energy. Okay, calculate the total energy that has to be supplied to move the 500 kilogram satellite from an orbit of radius this to this. So, effectively, as it's gone higher, the kinetic energy has gone down by 3.54 gigajoules, but we've also seen that the change in gravitational potential energy is equal to 7.15 gigajoules, so that's going to be the potential energy, and therefore it should be equal to, is that right? So that's gone down, but that has increased because it's less. Is that right? So that's, the kinetic energy has gone down by this much, but the gravitational potential energy has gone up by this much, and therefore the total energy is going to be the difference of these two things, and that's going to be equal to 3.61, is it? Gigajoules? Yeah. Okay, right. So we've got a good question here. This is right. Is it Arya? Is that how I say your name? Hopefully I've said that right. Basically, the question I was saying is that when you've got, if you've got like a big mass M and a small mass M, which is orbiting around it, you can basically derive the equation that says T squared is proportional to R cubed. But you do that by saying that T squared is equal to G M for pi squared R cubed. But the thing is, this is just the mass of the big thing here. If instead you had two things, which maybe that's M and that's M, and they're maybe orbiting like a kind of common centre, so maybe you've got like a binary star system, does this still apply or not? And I think that's a question that me and Zed Physics had, and he's got a proper physics degree, I've got an engineering degree, so this is something I never did at uni. So I think this equation here works when you've got a small thing orbiting a big thing, but we had a question about, I think it was like a comet and a small satellite on that comet, and I think we just had to make the assumption that all of the mass was concentrated in the big one. But yeah, that is an undergraduate level concept, and that's something where the question that we did, because it was an Olympiad question, it's designed for A-level students, I don't think it went into that kind of thing there. But I think what's really interesting about it, though, is when you talk to other people who like physics, is that you do realise that sometimes there are questions which are quite difficult, and it kind of just takes... and I think it's just kind of really interesting how it can take a concept that you kind of understand at A-level, and then it kind of just opens door to how it can be used in other things. So yeah, super interesting stuff. Right, so I would say the energy supplied would be 3.16 gigajoules, which is different to their answer that they've got here, actually. So they've just given it as the same as that change in kinetic energy, because they've used the total energy of a satellite equation. The other one says, what's this, 2.6? They gave, oh, here we go. Total energy supplied is 3.6 gigajoules, which is what I put. Same answer as in 2.5, but that's a different answer. So I think that's close enough. Basically, they've used some kind of approximation further on in the calculation. So that is a good enough answer. Okay. Right, 4 assumptions made in the molecular kinetic theory model of an ideal gas. Okay, right. Yeah, fair enough, Sam. Nice to see you. I know clips of 2021. I know you can't watch it. I know lots of people have maths. So I'm just doing this anyway. You can watch it whenever you want to. So if you want to come in and join in, that's fine. But yeah, this live stream is going to be up for the rest of the week until paper 2 is out there. I think the key thing here is you need to have the word negligible. So it might be there's the volume of the particles is negligible compared to the volume of the container. There are negligible forces between them. There are going to be perfectly elastic collisions. There's a large number of particles in random motion. Yeah, raved. Yes, this is what I talked about the other day. So something I talked about in my masterclass, and also wrote about in my daily workout. And for anybody in year 12 watching, you need to buy this book. This has questions that start in July. And basically there are questions that, so if you're a year 12 student, I've got questions that cover everything you need as you go from year 12 to year 13. So I would say that this is raved down here. So hopefully that's going to stay in focus. There are 5 things you could possibly say. You've got identical molecules that are in continuous random motion. So that's why they're identical. So that means they are of a similar size, or they're the same size. There are negligible forces between molecules except during collisions. So that means they don't attract each other. The volume of the molecules is negligible compared to the volume of the container. Then for E, we've got these perfectly elastic collisions between the molecules and the walls of the container. And also the duration of collisions is negligible compared to the time between collisions. So this thing here, if you want to get your phone out and take a picture of this or screenshot it, this is raved, and you can just have some of these assumptions for this kinetic model that we use for gases. So that came from the daily workout book 4, and I've got my summer job, which is to write and finish off the rest of book 5. But lots of good questions in here that hopefully, if I just kind of show you some things here, we've got, you know, questions about charges, there are graphs, there's things oscillating, and I'm sure if you're year 13, you'll kind of recognise lots of these things. I guess that one there could be similar to one of the questions that came up about cells in parallel. So yeah, this is my daily workout book 4, ideal for any little year 12 people watching. Do I reckon the PM2 predicted paper is accurate? No, I don't. I don't think it's a prediction. I just think it's the style of questions that are asked about in normal paper 2 exams. So I don't think it's an exact prediction. I think the word predicted made people download it and made you lot interested in watching me do it today. But I just think it's a good source of questions that are the type of questions that could be asked in paper 2 exams. In terms of level of difficulty, I'd say that, yeah, actually, to be fair, the level of difficulty is kind of fair, I think, for real physics exams. Yeah, there's going to be some easy questions, some difficult ones, but I think it's a fair level of difficulty. Right, we now have a sealed cylinder containing an ideal gas at constant temperature. Luckily, they've given us the temperature in Kelvin. When the piston compresses the gas, the volume is 0.5 and the pressure is this value. Okay, we now need to show this on a PV graph. So we know, of course, from Boyle's law that pressure is inversely proportional to volume, or PV is a constant, provided we have a constant temperature. And it says here that the piston is slowly pulled out. Now, if PV is a constant, we've got a pressure of 20 and the volume is 0.5. So the pressure times the volume is going to be equal to 10. So looking at this, when it's 20, that's 0.5. So 20 times 0.5 is 10. If we've got 10, we need to multiply that by 1 to get 10. When it's 5, we multiply it by 4. Is that right? Am I doing that right? 5 times 4 is the answer. And basically it's got to go through these 3 points as far as I can tell. So, is that right? Oh no, sorry. 5 times 2 is 10, isn't it? Thank you to people who are probably going to be pointing that out in the chat. And then we've got 4 times 2.5 is going to be the other point. Okay, yes, 5 times 2 is 10. Right, so my approach to this is, because it's a curve, I'm definitely going to be using a pencil. Going to move the paper around, and then let's see how we get on. There we go, like a boss. I reckon that's a pretty good curved line, so that I'm going to leave it there. The assumption made is that the temperature is constant. That was a great curve. Thank you so much. Temperature is constant. Thank you, Manavia. Yeah, so temperature is constant. Okay, I'm just going to leave that curve there for a few more seconds for you to appreciate before we go on to the rest of the question. Okay, yeah, it is true though that, like, I can do curves really well, but I'm really rubbish at doing 5 times something to make 10. Okay, right. Yeah, anyway, yeah, it didn't look quite right when it's doing that. Okay, so the next bit then, calculate the number of gas molecules in a cylinder. So there are lots of equations that could be used. The one I'm going to use, the ideal gas equation that says PV is equal to NKT. Okay, so this is one of the ideal gas equations, and this is because N is going to be the number of molecules. So N is equal to PV over KT. We can use any value of pressure and volume, but I'm going to make sure that I do it in the right units. So the pressure was 20 times 10 to the 4 pascals. The volume was 0.5 times 10 to the minus 3. K is 1.38 times 10 to the 23, I think. I think I should know this. 1.38 times 10 to the minus 23, and the temperature was 300 Kelvin. Okay, so making sure that temperature is the absolute thermodynamic temperature in Kelvin. Okay, so now we can just kind of multiply all of these together. This gives me an answer of 2.4155. So I'm going to give that as 2.4 times 10 to the 22 molecules, which I think is an appropriate answer, giving that to two significant figures, because we've been given the volume and the pressure to two significant figures as well. Calculate the total kinetic energy of the gas molecules. Well, from this, we can basically start with the equation that says, well, the way that they have it here is that a half mc squared is equal to 3 over 2 kT. Now, of course, that's going to be the kinetic energy of one particle. So the total kinetic energy is going to be equal to the number of molecules, n, times this kinetic energy, which is then 3 over 2 kT. So we need to multiply the number of molecules, which I'm going to use my raw data up here, my calculated value of 2.4155 times 10 to the 22. I'm going to multiply that by 3, multiply it by Boltzmann's constant. I shouldn't be going over the edge of the paper really. Times 300, divide that by 2. So let's see what the answer is then. So $150. That seems too nice a number, so 150 joules, and I think that would be an appropriate way to get it. So yeah, that's my approach really, just looking at how the kinetic energy of one particle is 3 over 2 kT, so based on the temperature of that ideal gas, and we just multiply the energy of an individual particle by the total number of particles to get the total average energy. Yeah, I think that's a fine question, isn't it? Right. Why did I equate a half mc squared? Yeah, so the question said, calculate the total kinetic energy of all the gas molecules. Now, this equation here basically says that the kinetic energy of one molecule is equal to 3 over 2 kT. Effectively, what this means is that the temperature of an ideal gas is directly related to the average kinetic energy of the particles. So if you've got something which is hotter, the particles on average have more energy, and therefore they're going to be moving faster. So that's why I kind of wrote that equation down, because that's the format that AQA give it in. And so the kinetic energy is just 3 over 2 kT. And then you just multiply the kinetic energy of one particle by the total number of particles to get the total energy. Hopefully, Octavian, that's making sense. Oh, an explanation one. Oh, right. So, okay, this is all right. Some of you might have seen something like this, but kind of this way round in school. So has anybody seen a jumping ring? Basically, you have a coil of wire that's connected to like a DC circuit, and then you have like another coil, just a single coil above it. And when you close the switch, we have a high rate of change of flux linkage, which means we have a high changing magnetic field. So we've got a high EMF being induced, which causes a big current, and then that current causes, in this kind of wire here, then a magnetic field which opposes this magnetic field, and then the two fields repel, and then it kind of jumps up in the air. So some of you might have seen a jumping ring before. Okay, MAE, thank you so much. Yes, saving everyone's grades. Well, basically, I'm going to be pushing all of your grades up, but I suppose there's lots of people who aren't watching this who don't know I exist. There will be people in your exam tomorrow who've never seen my videos, I suspect, at A-level. So I guess you guys out there, whoever you are, do have a bit of an advantage. Okay, explain why when the switch is closed, an EMF is induced in coil Q. So I guess a lot of the time, this is a great example for you to kind of write in bullet points. And also you can maybe quote things like Faraday's law, Lenz's laws, and so on. So we don't need to explain why it moves or the force on it. We just need to say when that switch is shut, why there's going to be an EMF induced here. Okay, Edward, no way. Undergrad engineering, good choice. What kind of engineering are you doing? And yeah, did A-level physics as well. Cool. Yeah, so when a switch is closed, okay, so basically when a switch is closed, a current flows in coil P, and therefore there is a magnetic field around coil P. Okay, then we can say that this changing, I could have probably written this a lot better, but this changing magnetic field as the switch is closed induces an EMF in coil Q due to Faraday's law. So I've now quoted the law that I'm going to be looking at, and then I can just write this down as the EMF is proportional to the rate of change of flux. And I think that's what the answer is really. Mech Eng at Bath. Great place, yeah. Bath is the place to be, isn't it? Mechanical engineering, great degree as well. I've seen a few. Occasionally, I do see people from Bath Uni. I think I saw somebody when I was in Urban Outfitters with my daughter, and yeah, they came up and just said hello. So I do occasionally see engineering people around Bath. So yeah, hope it's all going really well. Awesome. Right, yeah. I think that's basically it, really, isn't it? So we've got a current that flows in coil P, and therefore there's going to be a magnetic field around this coil, and that's a changing field as that switch is closed. And if you've got a changing magnetic field, there's going to be a change in flux per unit time, this will induce an EMF in a conductor in that field. I'm going to leave it there. The student notices that there's a force acting on Q after the switch is closed. State which direction this force is in. So the force is going to be... so which direction is the force in? I guess the force is going to cause this thing here to move off to the right. So again, we have that kind of sort of jumping ring if you had this kind of vertically. And it's going to go to the right. Somebody says that they need a comp sci version of me. The problem is, I know there's a few people doing it. Is it something in Dave, is it, or something? There's two people who do lots of stuff, but I think, yeah, there's still space. There's still space out there for more people to be making videos, especially about kind of STEM subjects. Can you prove this to the right? I guess there would be to the right hand. So you could. Let's have a think. So when you shut that, we're going to have a current going this way. So the current is going this way around the coil. Then we can use our right hand grip rule to think. It's hard to tell though, because you can't, well, let's say this is something that's coming like this. So that would make effectively the north end be this point and that the south end being like that. So it's a bit like a kind of solenoid. So let's imagine it comes up here and it goes around and it goes that way. So we've got this here being the north end. And then in the other thing, we're going to use the, I guess it's not really, I don't want to confuse people with the right hand rule, but basically we'd now have, this would cause, due to Lenz's law, that to be the north end and that to be the south end, and therefore in this coil we'd have the current going in the opposite direction, and that would mean then that so that's due to Lenz's law, that would cause that to be the north end and that to be the south end, and then you'd have two north ends or two south ends, they'd be repelling, and therefore it's going to go to the right. Yeah, so this right hand rule here I used was my fingers being the direction of the current going around a coil, and this here being the north end of that solenoid. Okay, right, question 4 continues on the next page. Sketch a graph to show how the EMF induced in coil Q varies with time. So, right, this is where so let's do it in the AQA format. So the AQA format says that the EMF is equal to N d phi by dt. So that's the way that they do it. So they're basically saying that the EMF is going to be proportional to d phi by dt, and that's going to be equal to the gradient of this line. So this is the thing that lots of students will take shortcuts with. I'm just going to use my ruler here, and I'm just going to draw some construction lines that go down the page. They only need to be faint, and of course if anybody marking your work sees this, then they'll know that you know what you're doing. So basically we've got our construction lines to show the different times. When there's no gradient, or when it's flat there's no gradient, so there's going to be zero EMF induced at this point. We've got quite a steep positive gradient, so I'm going to give a steep positive value there, and then we're going to have a lower value over here like this, and then the final thing to do is that effectively that increases and then it decreases, then it increases. Okay, and I think as well, what's interesting to note is this area here is going to be the same as this area over here. Okay, yeah, so there we go. That was my approach to this. So I said that EMF is positive when that was a positive gradient, using this formula here. Yeah, so I'm going to leave it like that for AQA. Using Lenz's law and Newton's third law of motion, explain why a force momentarily acts on both coils P and Q after the switch is closed. So, I guess I kind of explained a bit of it before, really, didn't I? So I guess what I said before was that when you've got a coil with a current in it, that's going to cause there to be a north and a south end within that coil, which then, due to Lenz's law, causes a magnetic field that there's going to be a magnetic field here that opposes the change that caused it when we have an EMF induced here, when that causes a current over here. And so, yeah, that's basically why we have the north end here and the north end there. So that's due to Lenz's law. And of course, if there's, by Newton's third law, as much as that is pushing on this, this is pushing on that with the same force, the same size, but in the opposite direction, which then results in it moving away to the right. So yeah, that's basically what it is, isn't it? But I'm not going to write it all out now because I think it's quite a long thing. So what's the mark scheme said that PMT put together? They said for question 4.4, I haven't actually looked at the mark scheme yet, so I'm kind of doing it. They said, okay, they've said basically you get a mark for stating them. The induced EMF in coil Q will flow. I'd say that the induced EMF in coil Q will cause a current that will flow in such a direction that it opposes I think that's not... Okay, I'm going to write it out. So basically the first one is Lenz's law. And I'd say that the induced EMF in coil Q will cause a current with a magnetic field that opposes the magnetic field that induced the EMF. Okay, so I guess that's my kind of description of why Lenz's law is important. Hopefully that's helping Charlie's. Okay, and then of course we've got Newton's third law. What did they say? They said about Newton's third law, I guess from Newton's third law, yeah, good points coming up in the comments. Yeah. Sorry, I'm saying your name completely wrong, and I know you can't really say it in the chat, but yeah, is that how I say your name? Sorry if I've completely messed it up. Yeah, you're saying that Lenz's law is closely linked to Faraday's law, yeah, and it's basically the minus sign. Yeah, cool, right. Newton's third law basically says that the force of P on Q is the same size and in the opposite direction to the force of Q on P, and it repels. Okay, so basically it's like a shortened version of Newton's third law here about the force on P on Q. It's the same size in the opposite direction as the force of Q on P, so that's like a Newton's pair of forces, and in this case that's a repelling force, and that's why it moves away. Okay, hello Miles again. Good to have you back after doing stuff last night on the stream with OCR. We've now got AQA questions, which I'm sure you can see are pretty much identical. So for anybody out there who was here last night doing OCR questions, the AQA ones are pretty much the same. Right, this shows a velocity selector designed to operate with positively charged ions. So they've got a charge which is positive. They're fired into at varying speeds. Two parallel plates 2 centimetres apart. So that distance is 2 centimetres. The grey area represents the magnetic field. Okay, draw the direction of the electric field labelled E. So the field would be where a positive particle, or the direction a positive particle would move. So if you put a positive particle here, it would move away from the positive plate and towards this one. So my electric field would be drawn with a ruler like this. So I'm going to have evenly spaced lines. Obviously in the exam I'd be drawing these with a ruler. So that's my electric field. And if you've got that which would then be causing the particle to kind of accelerate down, which would mean there must be a force upwards. So on the charged particles, the particles are going to the right. There's a force up, which means that they move in a straight line. So the field is going into the paper. So the B field would be drawn like this. So that's going to be my B field drawn as crosses. Is that right? Yeah, so that'd be my approach to that. So using Fleming's left-hand rule to work out the direction of that magnetic field, because if it's a velocity selector and the particles would be pushed down due to the electric field, they must be pushed up by an equal amount due to the magnetic field. Okay, show that where that the selected velocity of the particles is given by v equals e over b. So basically, if this is a particle, there will be a magnetic force due to the magnetic field, and there will be a force down due to the electric field. The force up is equal to BQV, and this force here is equal to EQ. I think that this pen is running out. I've done a lot of writing recently. And of course, lots of people are revising for maths tomorrow, but I know some of the physics people have come and gone, or the maths people have come and gone, but this will obviously be kept on YouTube for you all to find. So basically what we can do is equate these two things together, because if the force down is equal to the force up, there's no net force in that plane, and therefore it's just going to keep moving in a straight line. So we can say that BQV is equal to EQ. These cancel, and therefore BV is equal to E. So the velocity is equal to the electric divided by the magnetic field strength. So that would be my approach to that. Okay. We've then got a question saying the magnetic flux density is 0.5 Tesla. Selected velocity is this. Calculate the potential difference required across the parallel plates. So, okay, so what would be my approach? Okay, so my approach would be to take this equation here and say that VB is equal to E, but also the electric field strength is going to be the potential difference divided by the distance between the plates. And we were given the fact that the plates are 2 centimetres apart in the first part of the question. So we can equate the two things together to say that VB is equal to big V over D. So big V is equal to dVB. So we've got potential difference and we've got velocity. So that means the distance between the plates is 0.02 centimetres. The velocity, 2.0 times 10 to the 5, and that's 0.5 Tesla. So that's equal to 2,000. I think that's kind of one significant figure, but I think that looks to be the right answer. Okay, so I think we're doing all right. Let me just have a quick drink. Okay, that wasn't too bad really, that question. Explain what possible changes need to be made to the design to make it work with negatively charged particles. Well, I guess if the particles are negatively charged, if you had negative charged particles, they would be now going upwards towards that plate. So what you'd have to do is either change the direction of the B field by 180 degrees. So that's one thing you could do. Or you could have the magnetic field in the same direction, but just swap the direction of the electric field. So we can swap the direction of the electric field by 180 degrees. Yeah, I think that's all you can really do, isn't it? I don't know what else you can do for that third mark. I reckon there's only 2 marks available for a question like that. I can't see how you'd be given a third mark. So I'm just going to clear my desk. I've got lots and lots of bits of paper. So I dread to think what I spent. Okay. Somebody, Edwards, still now, this is etched into your memory. You still hate these magnetic scenario questions to this day. Yeah, fair enough. Okay, right. So this one. I don't think that's right in the mark scheme. I don't think you need to really talk about using Fleming's left-hand rule necessarily. I reckon they're the two things, they're the changes, I guess, really. Okay, right. Molybdenum, I think that's how you say it. Molybdenum, it's got a nice ring to it. Molybdenum 99 is used in nuclear medicine. One way of producing it is through the fission of uranium-235, which releases other fission products and neutrons. Why does the uranium-235 release energy? So this is just a simple question about uranium-235, which is the main source of fuel in most nuclear reactors. And basically, we've got something large that splits apart, and the average binding energy per nucleon after it's split apart is now bigger. Right, somebody says, yeah, there's a mass defect. Yes, cosmic, excellent. Somebody's just said that they've, you did good in paper 1. Well, if you did good in paper 1, you can do fine in paper 2, but you haven't done anything at all for paper 2 yet. What should you do in the next week? I would say every single past paper that AQA have produced for exploring physics. That's it. If you do 8 of those exploring physics papers, that's going to really help. Yeah, just get on with it. Just do the work, you'll be fine. Why does it release energy? So I guess my thing that I'm kind of sort of visualizing is this kind of graph where you have the nucleon number over here, and then you've got the binding energy per nucleon over here. And basically, as you split something apart to make 2 smaller nuclei, the binding energy per nucleon increases, and there's going to be this mass defect, and that mass defect is going to then release energy. So we're going to change some of the mass into energy. Okay, somebody says your teacher made you do a past paper every week as homework. Yeah, awesome teacher. That's the way to do it. If you want to get prepared for exams, then doing past papers every week is definitely going to help. Yeah, so basically, if the binding energy per nucleon increases, then that means that energy is released. So you release energy this way from fission, or that way from fusion. Okay, so we can say that the binding energy per nucleon of the daughter products is greater and this change in mass, which would be the mass defect, is converted or released into energy. All words to that effect. Right, molybdenum 99 has a half-life of this many hours before it undergoes beta- decay to form the metastable isotope technetium 99M. So the M here means that it's metastable, and that basically means that the nucleus is not stable and the nucleus is in a higher energy state. You know that, and this isn't really discussed too much in A-level physics, but you know how you can have electrons in different energy levels, and they can go to a higher energy state and they can drop down and maybe give out a photon of energy. Then I guess you get the same thing, but it's like the nucleus has like different energy states, and the nucleus is in a higher energy level, and as it drops back down to a lower energy level, it then emits a photon, in this case of gamma radiation. So a metastable isotope basically means that the nucleus is in an excited state. There we go. The nucleus is in an excited state. That's why it's metastable. That's why there's the M after that. Right. Blah, 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 blah. So lots of information here. Where do I find these past papers? Yeah, these ones are actually from PMT Education. If you go to the Physics and Maths Tutor website, you go to the main page that has predicted papers, you can download these. You just need to swap your information, like your email address, and that means they'll send this to you, and then you can have a look at this extra source of questions. I don't think these questions exactly will come up in the exam. I don't think you can predict what's going to come up, because having looked at any previous paper, there's always going to be some wildcards in there. But again, it's a good source of questions to kind of talk through and I guess just illustrate different parts of the course. I reckon these are easier. I don't know, I think I think the questions are easier, but they're not as well structured and written as a real exam, but they're good enough to kind of just do some more practice with. Okay, so basically we've got this molybdenum makes this metastable technetium, and then this then decays through gamma. Okay, this 99M is used in diagnostic imaging, often used in maybe a gamma camera, because we can see where gamma radiation is coming from. Is that right? No, it's used in a... Yeah, I guess you can inject this and you can see where it's coming from because it's just a source of gamma radiation. Why is it produced on site at the hospital rather than brought in from an outside facility? I guess the main reason is that we've got a very short half-life, and if you were to bring it in from somewhere else, by the time you got to the hospital there wouldn't be enough of this left. So the technetium 99M has a short half-life. So it has to be produced on site, but of course it's produced from this molybdenum 99, and that has got a half-life of 65.9 hours. So that's about what, sort of 3 days, and that means you can then transport that from where the nuclear reactor is to the hospital, and then you have like your supply for the week, I guess. Yeah, so it has to be produced on site. Otherwise, the activity would be too low. To use for imaging. I think that's something really. Yeah, so basically it's got a short half-life, so it has to be produced on site. So there's enough of an activity that it can be actually detected in the body. Okay, outline 3 safety measures a hospital. So I reckon this question in an exam would be a suggest. That they should adhere to keep staff and visitors safe from the radioactive decay of molybdenum and this. Okay, I guess you want to make sure that... there's so many things. I don't think you actually need to know the details of what you do in a hospital. I think you'd have to monitor staff, handling radioactive sources. And that would mean that you basically keep an eye on the dose. So maybe they have like one of these kind of badges that kind of has a piece of photographic film that is developed, and that can be then used to check their exposure. So you monitor the staff handling radioactive sources. I guess you wouldn't want to have the kind of room where you're making this in the middle of the hospital. You probably have it in a building to the side. Yeah. Yeah. Store in lead-lined boxes. Yeah. So that's a good one. Store in lead-lined boxes. I mean, there's probably a million things that you could be doing, including, restrict access to the area, for example. So that only certain people can go there who've had the training to go onto those things, so things that are kind of locked away. Yeah. Right. Yeah, so I reckon they're the kind of things you could talk about. Okay, right, we're now on to, what time is it? Oh, it's only an hour and a quarter, so that's not too bad really for doing that bit there. Right, so the first question, basically a GCSE one, isn't it really? So we've got a kettle, it's boiling water in 3 minutes. What mass of water is heated? So I'd be saying that the energy... Actually, does AQA, I think you use Q equals MC delta theta, don't you? So Q is equal to MC delta theta. So the energy supplied divided by the specific heat capacity divided by the change in temperature is going to give you the mass. Now, it's basically a 15... So the power times time is going to give you the energy transferred. But the power is going to be 1500 times 0.85, because it's only 85% efficient. We multiply that by the time in seconds, that's 3 times 60. So that's going to be the energy transferred. So that's 22950, and that means the mass is going to be equal to this energy transferred, 229,500, divided by the specific heat capacity 4,200 times the change in temperature, which is 80, because it goes from 20 to 100. .68. So my answer for this is C. So my answer is C for this. Is that the right answer? Yes, it is. I think it is, yeah. Right. What's this? Yeah, they should. I reckon. Yeah, basically, I think lots of schools last year, basically the 2024 paper 2 was too difficult, especially for the time that you had available to do the exam. Lots of people complained, the Institute of Physics complained, universities complained because it affected their students coming onto their course, and I know that from speaking to university tutors. Lots of schools complained, and I think that's why the 2025 paper 1 was actually fine, the one you did the other week. So I thought paper 1 from AQA was a decent paper, from what I've heard. Okay, right, let's see what people say. What is the number of CO2 molecules in 2.2 kilograms of the gas? So the number of moles is equal to the mass divided by the molar mass. So the number of moles is equal to the mass, 2.2, or 2,200 grams, divided by the molar mass, which is going to be, if it's a carbon 12 and an oxygen 16, that's going to be 28 grams per mole. Is that right? And so we can look at the number of particles as 2,200 divided by 28, so that's 78.6 moles. And then we're going to just multiply that. The number of particles is the number of moles times Avogadro's constant. So it's this number multiplied by 6.02 times 10 to the 23, which is 4.73 times 10 to the 25. So my answer for this would be D. Okay, is that correct? I'm hoping I'm right. Yeah, cool. What are people saying in the chat? Yeah. Yeah. Okay, right. Dust particles can appear to dance in a beam of light as they move randomly. What is the cause of this Brownian motion? Okay, so basically, this is because, although the dust is moving, it's moving because it's having collisions with the air particles, which, although we can't see them and they're very small, that's what's causing the large dust particles to move around. So I think, looking at this, that C is the correct answer, and so that'd be my answer for number 9. So this Brownian motion is, we see the large particles moving because they're going to be collided by smaller particles moving much, much quicker. Yeah, cool. Number 10. 3 gas particles are travelling in the same plane with velocities. What is the root mean square speed of the particles? So let's say then the value of the velocity is 3, 6 and 2. We're going to square all of these, so that's 9, 36 and 4. We're then going to sum that up, so that's going to be equal to 49. Okay, we're now going to take the average of this, and so the average is 16.33, and then we're going to square root that, which is equal to 4.04. So my answer would be A, which actually is the only answer it could be, because it has to be a number between all of these. So the only answer that could actually fit would be A. So that's my approach to that one over there. So basically what we have is, we've got the square root of the mean of the square of the numbers. And that's why it's an RMS speed. Okay, it's the square root of the mean of the square of all of the numbers. Okay, this all making sense so far? I'm hoping I'm getting the right answers. Like I said, I haven't really worked through these questions, so I'm hoping I don't get stuck. The gravitational potential difference between the surface of the planet at point X, 20 meters above the surface, okay, so here is the surface of the planet, and here we've got a point X, 20 meters above the surface. So that is equal to 16 joules per kilogram. What is the value of the gravitational field strength? Is that the value of the change in gravitational field strength? Oh. You may assume a constant gravitational field strength. Okay, I'm not sure what that question is really asking. I don't, yeah. So my approach to this question, gradient indicates gravitational field strength, A. So what would be my approach? Let me just think about this. 16 over 20, which is going to be 0.8. And that's because we've got delta, the change in V over the change in R. Yeah, so G is the change in gravitational potential energy divided by, so G is, yeah, so the gravitational potential divided by the change in distance is that. So it's 0.8. Yeah, sorry, I had a bit of a slow moment there. Sometimes that just happens. Yeah, so G is delta V over delta R. So that's the equation we'd be used, which is that one there. Okay, this one here, my approach is, and this is like a kind of question where we've got two identical objects of mass m. So here we've got m, and they're separated by a distance of r. Now we've got two objects of the same dimensions but twice the density and twice the separation. So now we've got things where r is now 2r. And if they've got the same dimensions but twice the density, that means if that's the mass of m and that's the mass of m, this is now a mass of 2m and that's a mass of 2m. So here the force is going to be proportional to m squared over r squared. Here the force is going to be proportional to 2m times 2m, so that's 4m squared over 2r squared, which is 4r squared, which is equal to m squared over r squared. So basically the force has stayed the same, and so my answer for 12 is A. Okay. Right, hopefully that's all right. Is that good? Yeah, I think so. The Saturn V rockets have a mass as great as 3 million kilograms. Determine the kinetic energy required to escape from the surface of the Earth. So we've got the radius of the Earth and the mass of the Earth. I would say that the effectively their kinetic energy is going to be have to be equal. Yeah, so basically the kinetic energy is equal to the gravitational potential energy when that goes to 0. So the change in that, this is, okay. Yeah, okay, it's escape velocity. Well, I guess at escape velocity, v is going to be equal to the square root of 2gm over r. And therefore, the kinetic energy is going to be equal to a half m v squared. So basically then, so if that's v squared is equal to 2gm over r, and therefore the kinetic energy is going to be equal to a half times m times that, so that's going to be equal to gmm over r. Is that right? I think. Yeah, people are a lot quicker than me. They're going B. So let's put some numbers in. 6.67 times 10 to the minus 11 times the mass of the rocket, so 3 million kilograms, times the mass of the Earth, so 5.97 times 10 to the 24, divided by the radius of the Earth, so 6.37 times 10 to the 6. Okay, yeah, so basically that's the equation for escape velocity. We can work out the v squared, and therefore the kinetic energy is just going to be a half m times this, which is gmm over r. So let's do some numbers. I'm getting 1.78 times 10 to the 14. So I think the closest one is B. So that's about, yeah, is that right? I think so. Right, or maybe I've made a mistake in my thing there, but I think that's the right answer, isn't it? So yeah, the answer for this, 13, is B. Okay, right. Okay, the diagram shows two charges, 60 millimeters apart. What is the distance from the two... Here we go, sorry. We've got two charges, that's 2 nanocoulombs, that's 8 nanocoulombs. What's the distance from the 2 nanocoulomb charge to the point between the two charges where the resultant electric potential is 0? So it's going to be a point probably closer to this one where the electric potential is 0. So this is kind of like that kind of null point in a field. Right, the electric potential V, let's just check the equation. V is going to be equal to 1 over 4 pi epsilon naught times Q over R. Okay, so basically we can say that V is proportional to Q over R, and this is where the strength of the field due to this is equal to the strength of the field due to that. They're just in opposite directions. So basically there's going to be a point where that's equal to 0, and that's because of 1 over 4 pi epsilon naught times 2 nanocoulombs over this distance. Let's say that's equal to R from here, over R minus this one here, which is 8 over, say, 60 minus R. Okay. And of course, that means that if this is all equal to 0, then 2 over R is equal to 8 over 60 minus R. So basically, that can all be 0, and then we bring, say that's 2, bring that minus 8 to make it plus 8 over 60 minus R. So there's that. So then we can say that 2 times 60 minus R is equal to 8R. So that's 120 minus 2R is equal to 8R. So 120 is equal to 10R. So R is equal to 120 over 10, which is 12 millimeters. So the answer for this then would be equal to D. So the point is going to be closer to this, and it's going to be 12 millimeters. I mean, I could have kind of converted these into nanocoulombs. I could have converted those into millimeters, but I just left it like this. So my answer for that is 12. Does that make sense? Yeah, hopefully that's all right. Hopefully that's making sense. Sorry, I've just gone on too much paper here. Two parallel plates have a potential difference between them and a distance d between them. What is the magnitude of the electrostatic force acting on a charge Q placed a third from one of the plates? So, let's go for green. The electric field strength is going to be equal to V over D. And the electric field strength is going to be equal to the force per unit charge. So if we equate the two things together, we can say that V over D is equal to F over Q. So actually then F is equal to VQ over D. And it doesn't actually matter. So here, this is the D that we're talking about. And actually that force is going to be the same everywhere between these two things. So here, the right answer would be F equals VQ over D. VQ over D. So here the answer to that one is B. So we'd have the same force because we've got the same electric field strength between the two plates. Do I do OCR GCSE physics? Yes, I've got videos that cover the entire OCR GCSE physics course, and you can find them over at gcsephysicsonline.com. And I will do some GCSE lives as well in the kind of run up to the exams quite soon. Okay, so yeah, there we go. But yes, and this one is really basically like an A-level live stream, but I will be doing some GCSE live streams. And of course, I'll also be here if you are doing GCSE and you're doing A-level physics next year. I've got lots and lots of stuff to help you over the summer. Right, how many more questions have we got? So this is number 16. We've got 1, 2, 3. Oh, we've got loads, haven't we? We've got another like 15 questions. Okay, everybody okay out there at the moment? Let's see if I've got anything left to drink. I've got no tea. I've got some water from last night, so hopefully it's all still fresh enough. Okay. Okay, an electric field is produced in the region between parallel metal plates. So here are my parallel metal plates. Plate X has a potential of 100 volts, so that's X. Plate Y is at 0 volts. The distance between X and Y is small, along the line X to Y between the plates. So basically we're looking at this line down here. Now there's going to be a uniform electric field between the plates. So the electric field decreases, and it doesn't decrease and it doesn't increase, so they're definitely correct. The electric field increases and then decreases. No. The electric field strength is the same everywhere between X and Y. Yeah, so if we were to actually draw in the field lines, they would look like this. And therefore this last one here is correct. Draw a diagram, it really makes the questions a lot more simple. No, I've not had Lucozade tonight. Don't just have lots of energy drinks before bed. It doesn't help you sleep. I've just had tea and water tonight. Okay. An electron is accelerated in an electric field by an electrostatic force. The direction of this force acting on the electron. So the electron. Okay, right. So if we've got an electric field, which is maybe positive to negative, and we've got an electron here, the electron will be accelerated. So the field lines go from positive to negative, but the electron will be accelerated in that direction. So again, this is my quick diagram. So the electron will be accelerated parallel to the field lines in the opposite direction to the field. Yeah, so the field is going down, but the electron goes up in this case, and therefore D is the correct answer, I think. Okay. The force between 2 point charges is F when they're separated by a distance R. so this is the two things, and then that's the distance of r, and now the distance goes up by a factor of 4, so this is now 4r. Of course, the force is proportional to 1 over r squared, because it's going to be equal to 1 over 4 pi epsilon naught q over r squared, but q's are the same. So we've basically, that's gone up by 4, and therefore the force is gone down by 4r squared, so that's 16r squared. So now it's a 16th of what it was before, so the answer would be B. So basically we've made them 4 times as far apart, but the field strength has gone down by a factor of 4. A small positive charge is moved from infinity to a point in an electric field. Which of these is incorrect? Okay. Okay. So I'd be looking at these, the work done per charge. That one looks correct, so that's a correct statement. What else is correct? The electric potential of the small positive charge increases as it travels towards the point in the field. I guess it would decrease, become more negative, so I reckon that that's incorrect. So I reckon, I don't know, I don't like this question. I don't think this is a nicely worded question. It's not clear. The graph of the electric potential against distance for the small positive charge, the gradient will equal the electric field strength. I guess that's true. So that one's alright. I reckon that this is the incorrect statement, B. Yeah, I reckon that's alright. Yeah. Okay. Do you know what? I don't like that question. I don't think it's a very clearly written question. So I'd ignore that too much. I think probably B is the right answer, but I'm not convinced it's a nice question. Yeah, so I think B is the right answer for 19. Okay, I'm going to put that to one side. Okay, we've now got a circuit with a capacitor. The switch is moved to position 2. This capacitor charges through the fixed resistor in 36 milliseconds. So basically 36 milliseconds is the time for the capacitor to be equal to half of its original value, which would be equal to 0.69, or natural log of 2, of the time constant. How long will it take for the energy stored to decrease to E over 16? So basically, again, it's not a nice question. Right, I hate capacitor questions compared to some of the other ones. Okay, so do I need that? Probably not. Basically, so the energy stored by the capacitor is equal to a half CV squared. So the energy is proportional to V squared. So basically, let's imagine at time 0, the energy was equal to 1. At time equals 36 milliseconds, we've now got V over 2. So the energy is now a quarter of what it was before. How long will it take for the energy stored to decrease to a 16th? Well, I guess after a 16th, it would go to, that would go down to V over 4, and therefore the energy would now be a 16th of its original value. So that's another kind of 36 milliseconds. So I think the answer for this is B, would be my approach. And it might be worth just kind of sort of visualising what's happening. We've got the different times. You've got V over 2, then you've got V over 4 at this point. Yeah, so I reckon this one here, it's 2, basically it takes 36 and then another 36 milliseconds to go from V to V over 2 to V over 4. When you've got V over 4, the energy is going to be a 16th of its original value. Okay, this one here, I don't think is the kind of question that would be asked about on an AQA exam, because I don't think this is really in the spec. So a conductor L moves a distance x through a magnetic field. So this is the length L. It moves a distance x and it's travelling at a velocity of v. So I guess the area swept out in a unit time. So this is going to be the area per unit time which is being swept out. And of course the EMF is equal to the change in magnetic flux over time, which is equal to BA over T. But A over T is going to be equal to, this area is going to be equal to Lx over T, because that's the area which is this length of wire times the distance travelled x when it's moving at this velocity, and therefore we can replace A over T with Lx over T, so that's equal to BLx over T. But of course the distance travelled over time is equal to its velocity, so this is equal to BLV. So here the EMF is equal to BLV, which is A. So that's my approach to 21, but I don't really think this is the kind of thing that would come up in an A-level paper. Is that right? Yeah, that's right. So that's my approach. We basically think about a wire of length L. It moves a distance x when it's travelling at a certain velocity, and this means this area per unit time is what has been swept out. Okay, and if we know the size of the B field, we times the B field by the area to look at the flux. Somebody else says only A has the right dimensions, David. Yeah, I suspect that would be true as well, wouldn't it? Yeah, I guess if you did some dimensional analysis, you could also work out which of those it would be. Cool, good stuff. Right, an electron moves perpendicular to a uniform magnetic field. The direction of the magnetic force that acts on the electron is... Okay, so the electron is moving perpendicular to a magnetic field. The direction of the magnetic force that acts on the electron is at right angles to the field, isn't it? Because it's going to be, if this is the electron, if it's moving at a velocity v, the force is going to be here. If it's an electron, so that would be that way. That would mean you'd have like maybe a field there. So it's going to be at right angles to the field. So I think C is the correct answer for 22. Okay. Okay, you've seen the video. Is OCR or AQA harder? I think they're both equally difficult, and both exams have difficult questions. I think that the OCR paper 1 this year was harder than the AQA paper 1 this year. So I think that they're both fairly comparable. Both of them have easy questions. Both of them have hard questions. Yeah, so I think the answer is they're about the same. Right, okay, right. The trace on an oscilloscope screen shows an AC voltage. The Y gain is set to 5 volts per division and the time base is 0.2. What is the correct frequency? So the time here, the time for one cycle is equal to 2 of these. And that's equal to 0.4 milliseconds. So because we've got 0.2, 0.4, and so the frequency is 1 over time, which is 1 over 0.4 times 10 to the minus 3. Which is 2,500. So the answer, it's not that one and it's not that one. Okay, the voltage. Well, I guess if that's 0 and the Y gain is set to 5, then that's plus 5 and that's kind of minus 5. And so the RMS value must be kind of along here, which is going to be between 0 and 5. So it's probably going to be 3.5 because it can't be 7. So here the answer for this would be B. Okay. All right, 24. I think we're coming towards the end at some point. I've got nothing left to drink. Right. A resistor R is placed in a DC circuit with a current I. It dissipates power P. So I guess we can say that P is equal to I squared R. A second resistor, half the size of the first, is placed in an AC circuit with an RMS current of 4I. What's the mean power dissipated in a second resistor? So the power would be the current, which is now 4 times as big, times a second resistor half the size. Does that mean, maybe then, does that mean it's got half the resistance, or is it like half the dimensions? I guess if the resistor was half the dimensions, like if it was half the length, it would have half the resistance. Let's say that it's just equal to R over 2. So that means the power then is 16 I squared times R over 2, which is 8 I squared R. So the first power and the second power is 8 times as big as the first one. So it would be B. Am I right? Yeah, cool. A transformer has 1200 turns on the primary and 700 on the secondary. The current in the secondary coil is measured to be 0.5. Do I think it's going to be a lot more straightforward this year? Potato Monk. Yes, I reckon it is. I reckon it's going to be fine. And yeah, a lot of people do have maths tonight. So I don't know how many people are actually watching this stream at the moment. There's probably only a few of you, but obviously this will be like probably watched over the next couple of days. But yeah, some people are doing A-level physics, but they don't do A-level maths, so they're the people who are maybe here tonight. Okay, what is the efficiency? Okay. So I'd just basically be writing out what... So on the primary coil, so we've got 1200 down to 700. So we've got 0.3 amps and 230. So the secondary potential difference is going to be equal to the primary potential difference times the number of turns on the secondary to the number of turns on the primary, which is equal to 700. Wait. So that's equal to 230 times 7 times 1200 over 700. Is that right? No, 700 over 1200. Sorry, you can see that my brain is kind of working quite slowly at the moment. So VS is equal to 134. And of course, I guess the efficiency is equal to the power out over the power in, which is going to be the secondary current and the secondary potential difference over the primary current and the primary potential difference. So that's going to be equal to 0.5 times 134 divided by 0.3 times 230. Okay, so basically that's the primary current and the secondary current and the secondary potential difference divided by the primary current and the primary potential difference. (0.97). which is going to be 97%. So here my answer for this would be C. Yeah, that's a bit of a messy approach. Okay. Right, the gold nucleus contains 79 protons, alpha particle, it's got this kinetic energy. What is the closest distance of approach of the alpha particle to the gold nucleus? Yeah, there's probably a quick way to have done that, I suspect. Yeah, okay, so what's the closest distance of approach of the alpha particle to the gold nucleus? So, if we know that the kinetic energy is equal to the electric potential energy, then this kinetic energy is going to be equal to that, which is 1 over 4 pi epsilon naught times Q1 Q2 over R. And therefore R is going to be equal to the two charges. So that's going to be Q1 Q2 over 4 pi epsilon naught EK. I think, is that right? So I think that's right. And this is because basically when the alpha particle basically stops and then moves round, its kinetic energy has been transferred to the potential energy between the two things. So basically that's when its initial kinetic energy, which it had, has now been transferred to the electric potential energy between the two charged objects, which is when it stopped. And that's going to be the largest distance that radius could be. So that's why I equated the two things together. Is that right? Have I made a mistake there? So this would be equal to 2 times 79 times 1.60 times 10 to the minus 19 squared. So that's going to be the charge on the alpha particle, the charge on the gold nucleus, over 4 pi times 8.85 times 10 to the minus 12 times 7.0 times 10 to the minus 13. Okay. Yeah, that's right. Yeah, so this is the electric potential energy between the two particles. Yeah, hopefully that's making sense. Yeah, and it's here, we've got that charge of 2 on the alpha. So if I put the numbers in, let's just bear with me. So you've got 4 times pi times 8.85 times... It is 8.85 times 10 to the minus 12, isn't it? Yeah, it is. .2 or 5.196 times 10 to the minus 14. So 5.2 times 10 to the minus 14 is that. Yeah, I think actually, having just quickly looked at this, there is a mistake in the way that they've kind of rearranged it, so they should be the other way round in the model solutions that PMT provided, which I've just had a look at. So yeah, so A, 26 is the right answer. I think that's my thing. Yeah, right. And yes, Sam, I'm still going. It's all right though. I think I should be done in the next sort of 10 minutes. A radioactive nuclide with a half-life of 6 hours has an initial count rate of 420. If the background count rate is 420, so basically the initial activity is going to be basically 400 at time equals 0. What would the average count rate of the source be after 24 hours? So 6 hours is a half-life. So when you've got the time equals 6 hours, it's going to have a count rate of 200, After 12 hours, it's going to be 100. After 18 hours, it's going to be 50. After 24 hours, it's going to be 25. So a fairly simple one here, and therefore, yeah, this one over here. Right, cool. Which of the following statements is incorrect in relation to the radioactive decay of a radioisotope? Well, that one's true. The process is random and spontaneous. That one is true. It doesn't depend on external factors. The activity is inversely proportional. That's not true, because if you had twice as much mass of a radioactive material, you'd have twice the activity, because you'd have twice the number of particles that could decay. So that one's not true. So therefore C is the right answer. But that last one also true, because gamma, if it's emitted, we still have the same number of things in the middle. Okay, right. Is this the last page? I think we are almost done. So it says a mix of uranium-235 and 238 provide the nuclear fuel in the reactor. The fuel decreases at this. What is the maximum power output? I've seen a few of these before, actually. So we know that the energy is equal to mc squared, okay? So the power, or basically the power, is going to be the energy per unit time, and therefore the maximum power is going to be the energy per unit time, which is equal to mc squared over T. So here we've got the mass per unit time that's changing into energy. So the power is going to be that mass, which is 5.0 times 10 to the minus 6 kilograms per hour. So we're going to divide that by 3,600 seconds. And we're just going to multiply that by 3.00 times 10 to the 8 squared. Okay, so that's going to be the mass per second that's being converted into energy. So we're just going to multiply that by that. Right. Power is energy per unit time. Cool. So (125) times 10 to the 6, so that's 125 times 10 to the 6, so that would be 125 megawatts. There we go, that's my answer. Yeah, okay. In induced fission, a uranium-235 nucleus absorbs a neutron. This forms the basis of nuclear fission reactions. Which of these is true? The control rods slow down the neutrons so they can be absorbed by other uranium-235 nuclei. I think that it's the control rods, what they're designed to do is absorb the excess neutrons. So they're not slowing them down. That would be where you have the moderator, so that's not true. The moderator absorbs neutrons. No, the moderator is just slowing them down. Each fission reaction produces great numbers of neutrons. Well, I guess that is true, because some of them are going to be absorbed before they get to other fissile materials. So, I mean, that is true, as in, like, you want to have n being greater than 1. And I guess you want it to be 2 or 3, because some of the neutrons aren't going to actually reach another fissile thing. So that is kind of a true statement. Thermal neutrons are required to induce fission reactions. Well, that's true. So I reckon this is true, but that one is kind of true as well. So that's true, but that's also a true statement. And if you've got 2 or 3, then that's fine. Yeah. Is that great numbers? I guess it's not a great number having 2 or 3. Okay. The most dangerous nuclear waste from a nuclear reactor. To be honest, the thing is actually the nuclear fuel with a long half-life often has quite a low activity, because not many things are actually decaying per second. It's often the things which have got a short half-life, which have a high activity, that can be more dangerous. But I would say that, yeah, you're going to have a whole range of half-lives. different sorts, alpha, beta and gamma, so I think that's probably the most true of all of them, because it's not just the long half-life stuff which is dangerous, it's often the short half-life stuff which has a high activity. Yeah. Which material was the moderator made from? I think it's often boron is used as a moderator in nuclear reactors. Yeah, so water or boron. Miles, thank you so much for putting that in the chat. Yeah, boron is often used as a moderator. Right, I think that's it. That's the end of the paper. Quite a long one, but not too bad. I think it was a bit quicker than the OCR one. Actually, that took me about 2 hours pretty much. And that was me like chatting all the way through it, which I guess is how long you have for a real exam. So that was just the predicted paper from PMT. I don't think that they're the questions which will come up. I don't feel it. I think they're good questions. They're standard A-level physics questions on the kind of topics that could be asked about in the exam, but you can't base your revision based on those predicted papers. But I definitely think it's a good source of questions that you might have worked through. But yeah, if you do want to do more physics with me, I'll be around tomorrow night. I'm doing an AQA workshop masterclass. It says on this big red thing underneath me, you can book a place on my website. I'm also doing another one on Sunday morning when I'm doing an AQA one as well. I'm also going to be doing stuff for OCR and Edexcel as well. And also, I've got practice papers because PMT didn't make papers for paper 3A, so you can buy practice papers. I've got 3A practice papers. I've got 3 of them available. You can find them on my website, or you can go to my online shop, where again I've got a full set of work solutions as well as like a mark scheme and like kind of real sample questions like you might get in a real exam. So some good stuff there as you're preparing for paper 3A. Yeah. But I hope all of you are having a good time, if you can call revising for exams a good time. But I hope they're all going well. If you've got maths tomorrow, I hope it's going to go well. Or if you're watching the replay, I hope that your maths exam went really well. So yeah, good luck everybody, and I'll see you all soon. Thank you very much. How do I stop this? Here we go.